team lead or something. Over here, you might just collaborate with the person. So the relationship between the two vertices actually matters. It's not just enough to know that they're connected. All right, so this is an example. This is another example that we kind of played with a while ago that actually treats, we took public data from various sources that deal with the legislature, the Congress. And you can actually model Congress itself and the work that it does as a graph. So you have a legislator. The legislator might sponsor a bill, or they might vote on a bill. The legislator might be a member of a party, might represent a state, that sort of thing. All these concepts are very, very easily, almost trivially, represented as a graph. Okay, so now I kind of alluded to this before, but when we're interested in graphs. Well, let me talk. So let's talk about Neo4j. So Neo4j, this is the Neo4j slide. So open source, it's an open source graph database. It uses a property graph data model, which I think is on the next slide, that essentially relates, or it essentially records or stores nodes and relationships, so vertices and edges, for people who prefer that terminology. It's a native graph database, which means that it's not overlaying the graph on top of another database. So you can do a graph in a SQL database, you can do a graph in a NoSQL database, you can do a graph, however. But Neo4j specifically is a class of graph database that doesn't, that actually stores the underlying storage mechanism is specific to a graph. It's not overlaid on top of another database. It uses the Cypher query language, which we'll see as it's in order to query the graph data, and it is open source, so you can play around with it. It's actually pretty fun to play around with, even if you're not going to use it for anything real. They have nice web graphics that you're going to see later, and it's pretty fun to just mess with. Okay, so the advantage of using a graph database, or one of the chief advantages, is that you can go from, just a rough sketch of what your data model is for your application, or what your data model looks like, into a production database without actually having to do any normalization. That's kind of one of the chief benefits. Now, ordinarily in like the SQL world or the relational database world, you would think of, essentially this is like an unnormalized ER diagram, right? And then if this was a relational database, each of those relationships would eventually possibly become a join table or something like that, or it would become a foreign key or something along those lines, depending on the type of relationship or whether it's a one-to-one or whatever. Okay. With a graph database, you actually don't have to go through that normalization process, which is kind of nice because it makes the data model a lot easier to think about for the developers, and it also makes it a lot easier to refactor because instead of having a lot of complicated, potentially complicated logic in order to do joins and stuff like that, in a lot of cases you just adjust your queries slightly, and we'll see Cypher actually lends itself to this. It's pretty neat. So we can go from, that's the totally unnormalized ER diagram, and that's the actual result of a query from the database. That's exactly what that's what it would look like. That query, specifically. That's what you get back. All right, so I said we'd talk about this. On a couple slides ago, we mentioned that the Neo4j uses what's called a property graph. And what we mean by that is there are two types of things within the database. There are nodes and there are relationships. The nodes represent objects in the graph, and they can have name-value properties. So the way you can think about this is each node can have a little JSON object associated with it, or a little dictionary or map or whatever. And they can also have labels. So in this case, person, the name of this person is Dan, but the label, or if like you're used to thinking about like an object hierarchy and object-oriented language, you could probably think of this without too much error as a class. Okay, so person is the class, and then the instance has name Dan, born, whatever, Twitter. And this is a different instance over here. The relationships are the links between the nodes, and they have a direction. In Neo4j, in some graph databases, you can have undirected edges or undirected relationships. In Neo4j, all relationships are directed, but you can query them as undirected. But generally, the relationship, so the relationship has a type as well, and generally the type of the relationship kind of tells you like what it means, right? So in this case, Dan loves Anne. Dan lives with Anne. Anne also loves Dan. In this case, you notice that this one is duplicated. Loves is duplicated there's two of them, because that's a relationship that isn't necessarily reciprocated, right? You can have an unrequited love. But if one person lives with another person, then by definition, that person lives with the first person, right? I mean, you can't really live with someone without them living with you. So we can actually treat this as undirected. But those have to be directed. Relationships can also have a little JSON object associated with them, so they can have information. So like here you could have like how much each of them love each other. Maybe you could do like a divorce detector or something. So you can actually associate information with these relationships. All right, so the Cypher query language is what Neo4j happens to use. And there are other graph data query languages. I personally really like Cypher. Some people have other opinions, but Cypher is essentially based on this concept of pattern matching. So if you look from like here to here, you see this a lot in Cypher where we're actually like drawing a graph with like ASCII art. So you're kind of like, it is literally an ASCII art graph. A little arrow, so Dan, and then a line, and then the square brackets denote a relationship, and then the arrow denotes the direction of the relationship, and then we have Anne over here. So this would be a create, so create the nodes and the relationship in the graph. So here we have a label. So we see the label is after the colon, and actually that's, I mean, there are programming languages that use a similar syntax for the type. I think Scalar does that. So if you want to think about this as like, an object-oriented type of thing, you can think of the colon as, you could put a variable in front of that to capture it, but the colon is like telling you what the type is, just like in the relationship. And then you have the property, or the little JSON object is a set of properties that are associated with that node or that relationship. So, all right. So Cypher allows us to express pretty complex concepts, or concepts that are actually simple, but in many cases would be complex in a relational database. It allows us to keep what's simple, simple. So there's the SQL query. Find all reports and how many people they manage up to 3 levels down. So there's the Cypher query and there's the SQL query. The reason, of course, is that in the SQL query, you're having to sort of embed the graphical structure in the query itself, right? You're having to join things. You're having to do joins in order to follow relationships. The database itself has no idea what you're doing. It just knows that you want to join these two tables and then look at that table, look at the result, and then maybe continue going. So find all reports, how many people they manage up to 3 levels down. that up to 3 levels down adds a lot of complexity over here. Over here, we can deal with it with this little syntax right here. In other words, we can say this relationship here, and again, it's a pattern, like a regular expression or something. We're saying there's a boss, and then there's a manages relationship, and then there's a subordinate. And there can be between 0 and 3 of these manages relationships between the boss and the subordinate. So that means that you could have boss, subordinate, 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 right, on down. So because the database understands that what you're dealing with is a graph, the query length, or the resulting queries can be a lot simpler. Yeah.
So I don't quite understand. With that query, wouldn't you get 6 levels down if you had a boss that went 3 levels to subordinate and 3 levels to report? Or I'm misunderstanding what that query is?
Yeah, the query is meant to be kind of like complex but easy to explain. It's kind of it's a little bit of a contrived query, but yeah, you're saying, like, I want to know the top 3 layers of the company. I want to know how many people they manage up to 3 layers below them. So, like, the boss is going to have the 3 layers are going to be counted, and then, like, the person down here, it's going to count 3 layers below them. They're not going to have their own reports because they're not in the top 3. So, yeah, it's a little bit of a contrived query, but it's not completely unrealistic. I mean, in the sense that, if you were like in a human resources department or something.
And that SQL query came from an actual Neo4j customer, so something that they were actually running in a report. So.
All right, so native storage and processing. So I've kind of alluded to this, so this will be quick, but the Neo4j relies on a concept called index-free adjacency, and what that essentially means is that in the SQL query that we just saw, you're relying on, that query would be just tremendously inefficient if you didn't have indexes in your database, right? So in order to go from one node in the graph to another node in the graph, you're hitting an index. In other words, you're going to another table and you're essentially filtering it and then joining it. Okay. In order to do that, you have to do an index lookup. Neo4j doesn't need to do that because it's specifically the on-disk storage structure of the data mean that they're just pointers, right? So on disk, these are just pointers. So you don't need to do index. You could do non-index lookups, but you're smart enough that you're doing index lookups, but you don't even need to do index lookups. You just have a pointer to the next node. So the Neo4j's sort of, or other graph databases that have this property rely on this in order to get more performant graph queries. So the idea is that the entire thing is optimized for data that is structured like a graph.
Makes a graph database is index-free adjacency, being able to traverse through the graph without doing index lookup. So the performance of your traversals is constant time for local graph traversals.
Okay, so and this is just a diagram of what we've kind of been talking about. In this case, we have the person who knows 3 other people. In the graph database, it's essentially stored just like it looks. In a relational database, you have to have a join table, and then you have to essentially do lookups, whether they're indexed or not, in order to get back this structure. Okay, so we have this person friend here, and then that's going to join this one and this one. So that corresponds to this relationship right here. In the graph database, this is just stored. They're stored essentially next to each other with, there's a pointer stored with this node that points to this node. So then it's just a matter of waiting for the disk to spin around again. Any questions?
It seems like the edges, like all your data, a lot of your data is in the edge. Is that right?
It can be. It just depends on
I've got information about your instances, but how those instances are connected is with the edge, and it seems like that's really one of the most important parts.
Yeah.
If the edges aren't programmed, or aren't put in correctly, so, or if there's loops, I guess.
Well, yeah, if you have like cycles, then you have to be careful when you query it, because yeah, you could end up with a very long or a very large query result if you have a cycle and you don't guard against it in your queries. So yeah, there are definitely there's still a lot of optimizations, and there's still there's a lot of performance tuning, sort of looking at what the query planner's doing and trying to second guess it and stuff.
But it's still more efficient because it's in the setup of the database rather than somebody having to do it every time they want to query the database.
Yeah, and that's the key, is that the database itself imposes the graph structure instead of you imposing the graph structure on top of something that's tabular. So yeah, that's the advantage.
Wouldn't it be easy to run into like circular loops or something?
Yeah, and that's actually, if we look at this, if we look at this query right here, we've got the like star 0 to 3. You can actually just let that be unbounded, and then if you have a cycle, or a loop, then you can end up with some very inefficient queries. Even if you're bounding this, if it's like 10 or something, you can end up with some crazy queries. But again, that's...
Although with cycles, so with Cypher, in a given traversal, Cypher only traverses each relationship once. So you would never end up with these like infinite cycles. You would just like complete the cycle once and then move on to matching the next path.
So to detect the loop and stop.
Essentially.
Okay, so yeah, I think we've pretty much hit all of those. Okay, yeah, so some things that people use this for. Fraud detection, and then is a popular one. There are a lot of banks and stuff like that. I think one of the coolest things, and probably one of the more common use cases, is real-time recommendations. So recommendations are a very common thing, like Netflix, Amazon, that kind of thing. And this allows a graph database or a graph engine of some sort allows those to be computed a lot more efficiently, and in some cases in real time instead of having to be pre-computed. All right, question. Okay, so we got some questions. So we're going to go on to the next. So Will is going to talk about a specific use case now. We're going to talk about recommendations.
Yeah, so that was sort of the intro overview. So let's dive into to recommendations. So like George said, we've all seen these on Amazon and Netflix. Here's some movies you might be interested in based on movies you've watched previously. Here's some books you may be interested in based on books you've read previously. And if you were to model these sort of things as a graph, you'd end up with a model that looks like this. So here's Will. Will purchased the Python cookbook book. Amelia also purchased that book. So if we want to generate recommendations for me, we could look at what else have people who have bought the same things that I've bought. So essentially you're sort of inferring this link from me to also the Python book, but pretend that's a different book. So this is sort of the second edition. This is basically the simplest sort of graph-based recommendation model that you can do. And to do that in Cypher, it looks like this. So this is just saying find Will, find books that he's purchased, then find other people that have purchased those same books, and look at what books have those people purchased that Will has not purchased, and recommend those to Will, because he may be interested in those. So this is how you can put together a recommendation engine in 3 lines of Cypher.
And this is like going back to the object-oriented kind of analogy. The instance variable name is Will, and then its type is person. And then you have another instance of that over here. So those are distinct instances.
Yeah, so I would, and because
because, so we talked about with the cycles and with Cypher only traversing one relationship once, we wouldn't traverse back to Will when we look at other people that have bought the same books because we've already traversed that once. So that applies in cycles, it applies here too. So let's look at some real world data to walk through some examples of how we can do things sort of a bit more interesting. So let's take Meetup, meetup.com. So I know everyone here is a Meetup member. I know you all have at least looked at the page because we use that for registration for the conference today. But if we think of what type of recommendations Meetup generates, so Meetup generates recommendations for groups. So if I go to my group page, I can see, okay, well here's a meetup that I'm a member of, Montana Programmers. Now here are my suggested meetups. So these are other groups I might be interested in. And a meetup doesn't just pick these at random. They have to choose things that are relevant for the user to drive engagement into their site. Otherwise, it seems kind of senseless just show things at random. There's a limited selection of groups. So Meetup is recommending groups. They're also recommending specific events. So you get occasional emails recommending a certain event. Meetup can't just spam you with every single event coming up because then you would just cancel your email subscription. So they have to have very targeted things that are actually relevant to you to choose to send you these email invitations. And so these are some of the recommendations that Meetup is making. What we're going to do is grab some of the data from Meetup and see if we can replicate some of these in the next 15 minutes. So if you think of the data that's available for Meetup, we have groups, we have events, we have members, you can RSVP. So here we see the events for Montana Programmers, we have RSVPs for events. Groups have topics as well. So Montana Programmers is about computer programming, web technology, internet, all of these things. So this is all data that's available through the Meetup API publicly. So we just wrote some Python to scrape this data. All the code's online. You just need a Meetup API key. And so basically what this does is it goes out to Meetup API and says, show me all groups near, in this case, near Missoula. And then what it does is it sort of crawls out through topics from those. So it searches for other groups that share the same topics that we found near Missoula. And so in theory, this should crawl out and get a pretty big Meetup group for the state. And then we imported that into Neo4j, modeling this data as a graph. So this is the data model that we ended up with. We have nodes for groups. Groups have a topic. We have nodes for members over here. And members, when you sign up for Meetup, you can choose from a bunch of different topics that you're interested in. So members are interested in a topic. Groups have a topic. Members can be a member of a group. Then we have events. So events have some venue, commons. Members can RSVP for an event. The group can host the event. And the final piece is this friends. So there's no social component to Meetup yet. But what we did is we looked at people that attended events together, and we said if you attended at least 3 events together, then you probably know this person, because this is the whole point of Meetup, is to make friends, meet new people. So then we sort of inferred these social connections and created this friends relationship between members if you attended at least 3 events together. So before we jump into looking at some recommendation queries, I just want to sort of give a high-level overview of 2 different extremes for generating recommendations using graphs. The first one is content-based. So this is things like If I watch a Western movie, okay, what are other Western movies you might be interested in? You can do that across multiple topics, but that's the basic idea. And then the other extreme is collaborative filtering, which is taking into account the interests of people similar to you in the group. So in the context of the meetup data, this would be, who are my friends in meetup that are most similar to me based on events that we've attended together, and what events are they going to? Those are events that I might be interested in. So these are the two extremes, but really most recommendation systems are some blend of both of these. So just keep that in mind as we jump in here. So, bigger. So this is the Neo4j browser. So this is sort of a workbench for interacting with Neo4j. You can write Cypher queries and visualize them in here. So I have Neo4j running locally. We also have this thing called a browser guide. So we're going to type :play. Okay, so and so these guides, these are just written in HTML. We can embed some graphics and Cypher queries just to sort of to walk through things here. So this is available online. So in the slides, you can download Neo4j and just load this guide to walk through the data. And I'm not going to go through the import because I already ran this to import the data, but just want to talk about a couple of things for importing data into Neo4j. So the Python scripts that I showed earlier, the result of those are some CSV files. And Neo4j has some great tooling for importing data in CSV format. One of those tools is this load CSV. So here within Cypher, we're loading a CSV file, and then we're creating group nodes out of rows of a CSV file. And so we use that similar approach to go through adding topics, and then adding members, interests of the members, adding the events, the venues, and then this is the piece for inferring the social graph. And that is the import piece. So again, I already ran that. Let's just make sure we have the data in here. So this is just a query to look at our data model to verify we actually have what we expect. So this is the same data model that we were just looking at. So that looks good. Okay, so let's write some actual queries here. So we saw some basic traversals, examples of looking at the books and stuff. So here's one with an aggregation. So this is answering the question, what's the most popular topic? So of all of the groups that have a topic, what topic appears most frequently? So here we're just matching on this pattern where something has a topic. We're not specifying that it's a group that has a topic because we know that's the only thing that can have a topic. And then we're doing this aggregation count and returning topic names. We have this implicit group by whenever we use an aggregation, so we'll end up grouped by topics. And it turns out that dog hikes and hiking and software development, these are all the most common topics that show up for meetup groups in Montana, which makes sense. Okay, so here's our first sort of recommendation query. So if we want to find similar groups, one way we can define similar groups is by topics, so overlapping topics. So this query is going to find the Montana programmers group. It's going to traverse out to the topics, so the top line. What are the topics of Montana programmers? And then find other groups that have those same topics. And then it's going to aggregate on the group name and counting the number of paths there. So essentially this is going to return a list of other groups that we might be interested in if we're members of Montana programmers, based on number of overlapping topics. And we end up with Google Developers Group Missoula that has 3 topics in common: software development, JavaScript web development, Missoula Entrepreneurship Meetup, and then the original Missoula Entrepreneur Meetup. What the story is there. Okay, so that's our first sort of recommendation query for groups. Let's explore the graph a little bit more just to get an idea. So we can find ourselves in the data. We should all be in there, actually, since we're all registered for Big Sky DevCon. But let's look at me. So this is going to find me in the graph. It's going to look at all of the groups that I'm a member of, and then all of the topics that I'm interested in, and just return that graph so we can get an idea. So here I am, interested in software development. Montana Programmers has topic software development, so that's good. Here are the other things I'm interested in. So you can see how this workbench works, sort of for visualizing your results, both as a graph, but then also for doing aggregation, returning tabular data. We can also get tabular results. Let's get these because we're a bit short on time. So let's jump to a bit more complex recommendation query. This one is actually the same one we just saw. Let's look at events. So this throws in a ton of stuff. It's sort of jumping way ahead, but basically, so we recommended groups based on common topics, but we also want to be able to recommend specific events that you might be interested in, even for groups that you're not a member of. And there are lots of different criteria that might go into choosing whether or not you're interested in this group. So we need different ways to score that. So what this sort of monster query is doing is saying, okay, let's find me in the graph. So we're going to generate recommendations for me, and then we're going to look at all events within 7 days. So Neo4j doesn't have a date time type. Instead, it typically uses timestamps, like milliseconds since the epoch, something like that, stored as a long. So we want some time range. We just do these inequality queries. So here we're saying filter on events that are 7 days from now. So seconds, minutes, hours, and so on. And then we're going to see, well, are you a member of this group? If you are, we'll alias that to this myGroup variable. And then we're going to see, are there overlapping topics? So does this group have topics that you're actually interested in? We'll collect those as well. And then we will also see if you've been to events that this group has hosted before. And then here we're scoring these things. So we create the score that is 5 points if this is a group that you're a member of. We add the number of common topics, so 1 point for every topic that it has that you're interested in. And then subtract a point for every day in the future, because that way we're recommending things that are fairly recent, or coming up fairly soon. You don't want to recommend something that's like a year out in advance. That's not very useful. And come up with one recommendation for me, and that's to hike the Rattlesnake Wilderness, the Missoula Hiking Meetup. So we can see this has 3 topics that I'm interested in. It's 1 day out, so it has a score of 2. So you can see how we can look at lots of different things for generating these recommendations. We can also take into account location. This is more of the collaborative filtering approach. What this is saying is find all of my friends, and then one thing I didn't talk about is we saved a similarity score on this friendship relationship. So this is basically like how similar is this person to me based on the type of meetups that we went to. It's a card similarity, which is like a set comparison. So what this does is says find 10 friends that are most similar to me, and then find what they have RSVP for and recommend those to me. And we get the after party that my one friend will be at. So, that's a pretty good recommendation. In the last couple of minutes here, I want to talk just a little bit about how Neo4j can work with other analysis tools. So who here uses Python? A few people. What about Python data tools like pandas, scikit? So Python has really good tools for data analysis, and Neo4j works really well with those. So this is a IPython notebook example showing how we can call Neo4j from Python using the Python driver. So what we're doing here is just connecting to Neo4j, and then this is just sort of our hello world to make sure we're connected. We're just looking at groups and topics, so similar query that we saw previously. But what we want to do is we want to be able to cluster our topics. So if we can sort of find similar topics, we can take that information into account when we're making recommendations. So we're going to use the iGraph library from Python. Anyone use that for graph algorithms? Okay, cool. So iGraph has lots of graph algorithms. One of those is a community detection algorithm. So what we're going to do here, and I'll just go through this pretty quickly, is we're just pulling out topic co-occurrences. So we want to know, for all groups, what topics are occurring together, and we're scoring those. So we end up with sort of another graph here where we have hiking and outdoors have a similarity of 3 because there are 3 groups that share those topics. Then we can use iGraph to do a community detection algorithm. Basically what that does is tries to group these topics together in clusters of similar topics. And we can write that back to Neo4j. So this is here we're creating cluster nodes and connecting topics to those clusters. So then if we go back to Neo4j, let's just look at our clusters here. So we end up with 8 clusters, and if we expand out on these, you can see that this makes sense pretty quickly. So here are here's dog walking, pets and animal topics. They're all grouped together. Here's like swing dancing, tango, Latin dance. This cluster is sort of all the startup and business stuff, and so on. And so we can take these clusters back here to the guide. We can take these clusters into account by saying, okay, what clusters or what topics are you interested in? What are other topics in the same cluster? And recommend both those topics in groups that have those topics. So if we run that, we can see other groups that I might be interested in based on these cluster topics. Cool. So that's we're out of time here. We have 2 minutes. I think that's all that we'll cover. Are there maybe 1 or 2 questions to take at the end here? Yeah.
So the first method seemed like just like a complicated intersection of a Venn diagram for finding
overlapping topics.
Yeah, which is not good. But to me, the most important part for the second method is actually the metrics.
Mm-hmm.
Because if your metric,
everything's scored.
does that sound right? It's that metric that determines
Yeah.
really everything.
Yeah, so like in real like production systems, and George mentioned this a little bit, like what's really useful about graph-based recommendation systems are, one is that you can do them in real time. So typically a lot of these recommendation systems will like batch compute these and then serve pre-computed recommendations. And if you say like, I've already bought the product or read the book, or the product isn't in stock anymore, things like that, then that's a really bad recommendation. So really that simple, just like here are the overlapping topics, you can do like on the hot path for a web app, but also take into account things like inventory, things like logistics. Can you actually get this to this person? Is this a promotion? You can factor all of that in real time. So that's sort of like a simple example of where to start. But yeah, and then blending methods to come up with some metrics for how you weight that as well.
It's kind of the idea of like you're sacrificing maybe a little bit in like a rigor or maybe accuracy or something, but you can do it much more quickly. Therefore, you can really get
It seems like there's two things. You've got the database, and on top of that is the metric. The interconnection between chemical reactions in our cells, you can state that, but we don't know the rates at which those are occurring. Once you put those rates on there, all of a sudden now you can see feedback loops, you can see the way in which the cell's actually behaving. But then you can do that with company dynamics. You can say, look, these stimulants, these people are communicating with each other, but not at the same rate. You can do the same thing with these purchasing rates and these viewing rates, and the way in which people are actually interacting with the database. And you actually start incorporating these weights, the amount of information you can get out, and your predictability can be orders of magnitude more efficient.
Yeah, and so that's things like, which I really went through quickly here, but with the friends relationship is like George and I aren't just friends. There's some score associated with that based on like the similarity of the events that we've attended, and so being able to take that into account and factor that into your computation of just a metric for your recommendation. Cool. I think that's right about time. So.